Everybody. I hope you're doing well today. I'm here to talk about Substrate. My name is Jacques Nadeau, and we're going to be talking about really how we can rethink the decomposition of databases. So let's get started. Quickly, just about a little bit about myself. So I've been relatively involved in both open source and commercial endeavors. On the open source side, I'm co-creator of Substrate. I am also the co-creator and original PMC chair of Apache Arrow, very involved in that for a number of years. Also got involved with the Apache Calcite project, an open source compiler. Before that was even an Apache project about 9-10 years ago now. I'm also the co-creator and founding PMC chair of the Apache Dro project. So I've been working in data and open source for quite a while. On the commercial side, I recently started a new company. I'm CEO and co-founder of Sundeck, which is a company that's about 6 months old, focused in data analytics. I'm also the CTO and co-founder of Dremio, was there for the first 6 years of that adventure. Jumping in, so when we think about data decomposition and database decomposition, I think that there's some really important things to focus on. And really, there's some really sort of fundamental changes that are occurring. The first is that data lock-in is really disappearing. And it doesn't mean that there isn't places where it's hard to get at your data, but the world of like, hey, I put something in a database and now that's the only way to access it, are going away. And I think that there are two different sort of undercurrents that are driving this change. The first is that we really have shifted towards cloud storage as the system of record. So dropping something in an S3 bucket or an Azure Blob Storage has become the standard way to store data. The second thing is that we've really seen a substantial rise in table formats, right? So like the projects like Apache Iceberg, Apache Hudi, and Delta Lake all basically drive towards treating cloud storage as not only a system of record for objects, but also a system of record for tables with updates, deletes, and whatnot. And so that's really changing the perspective people have on data lock-in, right? Now that my storage is available to many systems, that I can have transactional consistency and snapshot isolation from many different systems, all of a sudden that becomes a really sort of strong way to store data. It's not the only way people are storing data. People still put data in systems that are have private storage, but more and more the system of record for data, so that the gold copy of that data exists in this common format that many systems can access. The second thing that's really changing is that we're starting to see a breakdown of the coupling of API and compute. And so there's some really interesting dynamics around this, right? So interesting event that happened a little over a year ago was Databricks launched the Photon initiative or project or technology, which was really something drastic, which was Spark people, the people who built Spark, saying, you know what, the fastest way to run Spark now is no longer Spark, it's actually this new proprietary component. But what's interesting about that, right, is it's abstracting away the idea of the API that is Spark versus the implementation of running Spark, right? And we see some similar initiatives elsewhere. So, for example, the Velox team at Facebook, thinking about the same kinds of dynamics in the context of both Spark and Presto, and saying, hey, you know what? We want a higher performance compute engine, and we want that available across multiple different systems. So a very powerful paradigm there. You also see Voltron Data pushing a lot of the same ideas, basically saying like, hey, let's start to decompose this and build a new Apache Arrow C++ compute engine that's highly performant. So you have these generic compute kernels that are starting to rise up. And you also have compute engine specialization, right? The rise of things like Apache Pinot and Druid and ClickHouse, which are specialized compute engines that are really, really good at a subset of workloads. And so all of this is really changing how the world works. And we've kind of seen some really interesting sort of development around this. If you think about, going back to the original state of warehouses and warehouse appliances, right? The Teradatas and the T's of the world. We had very coupled infrastructure. It was built on-prem, it was installed. You got a big server rack installed in your data center. And we shifted, right? There was a pretty big shift towards cloud warehouses, right? Snowflake has done very well with the cloud warehouse paradigm. Redshift also did well there. Still relatively coupled in that most of the components are internal components that are, distinct inside that technology, but not something that can be composed of by external organizations. And really the big shift that's happened, as of a couple of years ago is what we call the lake house now, which is a separation of storage from compute, right? And so you think about the query engines, whether that's Spark or Dremio or Trino or something else, and they're working on top of tables and catalogs that exist external to them. And this has gotten more and more blurry as technologies like Snowflake have adopted Iceberg as a native table format as well. And so the warehouse lakehouse separation has gotten indistinct. And I think that what we're moving towards, and this is my expectation of where the world is going over the next few years, is we're moving towards what I'm calling the fair house, which is the idea that API now will start to get decoupled from compute in the same way that storage has become decoupled from compute. And the reason I call it fair house is because all of a sudden, even if I choose to use a particular API because I'm comfortable with that, or that's because that's the most appropriate way to express that set of computations, I can still choose a different engine to solve my problems. And so that allows me to pick an engine that is most efficient or cost effective, or has a particular set of characteristics like low latency or high throughput that's most effective for my particular workloads. So I get the best of each world. So I can choose and mix these things to make sure that I have an optimal situation. So when you think about this, right, like the best of breed decomposition, it requires these sort of separate components and how these separate components work together. Well, as we all know, a database is not as simple as some storage, some engine, and some API, right? And I'm going to say, well, a slightly more complex version of that looks something like this, right? Which is you have an API. The API allows you to express instructions, which are handed to a compiler. The compiler then takes instruction, turns that into a new set of instructions, goes through several layers of transformation and optimization, potentially, thinking through how to slice this up and run it in a distributed way, and then passing that information on to an engine. And then an engine may in fact interact with storage, but more and more we're starting to see, various levels of computational storage, from the very, very simple computational storage of, say, something like S3 select, where you can basically push some simple predicates down to the underlying storage, to things that are much more complex, where you actually have powerful computational capabilities attached to SSDs that some companies are working on. And so basically you want to push those instructions down, and then you're starting to bring back data. You bring back data from the storage layer to the engine. The engine is obviously going to do a bunch of processing, and then it's going to bring that data back to the actual end user, the API, to actually consume at the end of the day. Now, that's a little bit more complex model. Obviously, there's a lot more sort of components that go into actually building a database. You've got schedulers and all sorts of other kinds of concepts there. But when we think about at least this sort of simplified model, one of the things that I started working on about 7 years ago was the Apache Arrow project, right? And it really went at the right-hand side of these sort of intermediary capabilities, right? Was, hey, let's come up with a high performance representation of data for in-memory, not just something that's on disk. And we want to do this for two reasons. We want to do it, one, so that we don't have to keep spending time independently building high performance algorithms for data, right? So what was the case when Arrow came out is that every engine had its own internal representation of data. It may have been very much the case that some of those representations were similar to each other, but there was really no way to have any interoperability between those things. And so when we sat down and thought about the problem, it became clear that interoperability needed to start with a high-performance processing representation, because if you don't have a high-performance processing representation, then there's always going to be this choice to convert from the interoperability format to the internal representation. And so we actually had to start by defining an internal representation, but then once we defined a high-performance internal representation that was also wire friendly, then we could also have a pattern that moves between different systems. And so as you've seen over the last 6 or 7 years, Arrow has, I think, done very well at sort of taking on this space and solving this problem. And now we have a lot more components that we can stitch together with the use of Arrow. Now, on the left-hand side, how do we solve this? Well, right now we don't really have a solution. And that was really the idea behind Substrate was, hey, let's come up with an independent representation of instruction, right? And there are several different layers that this instruction can occur at, right? You've got sort of your API level instructions, which are kind of a logical representation of what you want to do. You've got something that's coming out after the compiler has worked on it, which is much more close to a physical concept around what we want to do. And then you also have potential instructions that you want to pass down to that computational storage to try to accomplish additional goals at that storage level, right? And so being able to have those instructions as something that's formalized then allows us to innovate further on having these components independent and yet work together. And that really comes to sort of the start of Substrate and what it's about. Well, I think it comes from sort of two main thoughts, which is one, there's this abstract need, which is that the more you can decompose these things, the more that you can drive innovation. And so two inspirational technologies that I think sort of formed some of the thoughts about Substrate were one, the JVM and the JVM concept of JVM bytecode, right? That allowed a bunch of interesting innovations at the front end and the back end independently within the Java ecosystem, right? So you've got things like Scala and Clojure and Kotlin at the front end. And then you also have things like Dalvik and Graal at the back end, which both sets of things can benefit from the fact that they're interacting with a common representation of how you want to do compute. Now, these are very generic compute concepts, whereas Substrate is much more focused on data processing, but the same concepts apply, which is that I want to be able to think about things independently between the front end and the back end. Another example of this is LLVM-IR, right? With the LLVM-IR, all of a sudden there were some really interesting things that occurred, right? So one is that I could be very creative about coming up with new languages, and we see lots of new languages that are built on top of LLVM. But because I'm targeting that intermediate representation that LLVM provides, I can have a high quality compilation experience and high quality code at the end of the day, even if I've come up with a pretty new and unique way to express that code. And the same thing has happened in the back end with WASM, which is really exciting, which is that like once you have that intermediate representation, you can now say, okay, well, let me target completely different kinds of compute paradigms, like a WebAssembly based VM. And by having that against a standardized intermediate representation, all of a sudden now WASM can claim 17 different languages or something like that that are natively supported because they happen to all work with LLVM, which is exactly what WASM works with as well. So that was the abstract need of saying, hey, let's figure out ways to drive additional innovation. The concrete need was about solving real problems, right? So there was a couple of different conversations that I was involved in I thought were very interesting. The first is that there was a conversation that I was having last year amongst other people in the community in the Apache Iceberg project, talking about the ability to have a common representation of views. So Iceberg is really nice as a common representation of data tables. And you really can say, okay, well, once I define a data table, it can be used across many different systems, and you still get consistent results from what's in that table. Unfortunately, with views historically have been defined based on SQL, and every different system has a different SQL dialect, which has variation in how things are expressed. And so if you want a common representation of views, you need something new to solve that. And so when we started talking about that, one of the discussions was, hey, can we come up with a more structured format for solving that? The second thing was inside of the Apache Arrow project. So the Apache Arrow project actually has several different compute engines. It has Apache Arrow Gendiva, Acero, and Data Fusion, which are all different approaches for how to solve sort of generic compute kernels. And as we were in the community talking about these different approaches to things, we realized that we didn't want to have to build SQL parsers or data frame APIs for each of those independently. And so we were talking about how can we have a standard representation of what we want to do in terms of compute, independent of the particular engine that's going to implement that. And then lastly, as I mentioned before, have been involved in the Calcite project for a number of years. And one of the observations I had is that Calcite is a very, very rich set of capabilities. But right now, it's fairly tightly coupled into the JVM. And so if you're in a non-JVM context and you don't want to really work with the JVM, it's very hard to access the Calcite capabilities. And so it was also this interest of saying, like, how can we potentially expose Apache Calcite in a way that makes it much more available to people who are working in other environments than a Java environment? So those are the kinds of needs that occurred. And out of that came this Substrate project, which we describe as a cross-language serialization for relational algebra. Interestingly enough, it's just about 1 year old now. And there are a bunch of integrations ongoing. We have about 30 contributors from multiple different companies, from small companies focused on data-specific things to large companies like the web scale, the cloud compute companies. And the real goal here was, let's define a well-formed, well-defined cross-language specification for the compute operation specifically against data, okay? and really sort of solving a bunch of these problems that I've just talked about. Allow different kernels and engines to arise and plug into existing components without having to re-implement a bunch of complex integration. Allow people to come up with new ways to express, compute languages, new ways to express how I want to do a computation. Because if you have these things coupled, it becomes very difficult for a new innovation to occur, because you basically have to build a giant engine, including both the APIs at the front end all the way down to the low-level computation in the back end. So we really wanted to say, like, hey, let's figure out new ways to drive this innovation. And so when we started the project a year ago, we put together this slide, which was some examples of different ways that we'd like to see Substrate used. And so, for example, like, hey, if I want to use Python and interact with something like IBIS, can I use that, but then target our arbitrary compute engines on the back end? Or if I'm using dplyr and R, can I also target different kinds of systems in the back end? Can I use the various forms of SQL that Calcite supports, including its own syntax, as well as several different syntaxes supported in the Babel parser? Can I use Presto SQL or Scala against Spark to be able to express different compute operations, but then take that and transform that? On the right-hand side, as I mentioned before, we were thinking about, like, how to use iceberg views to sort of translate these things. And then down below, once you have these different ways of expressing a representation of computation, how can I actually target the underlying infrastructure to do that? So these are some of the examples, right? So, there might be different engines that I want to run this on based on the capabilities, or maybe, pre-commit costs, pre-commit spend I have at a particular company that has some of the capabilities. And so those are the integrations. And so when we sat down, we said, okay, well, how do you build a project like this? And really, we started with what we did in the same in Arrow, which we said, this needs to be a specification first project. It can't be an implementation first project. And it needs to be a specification first that's language independent and serializable, right? So one of the things, it's very similar in some ways to Arrow, but in some ways it's very different, right? So one of the big key concerns in Arrow is that you're going to have a large amount of Arrow data, and you don't want to have to constantly kind of transform that. And so the wire representation is the representation. In the context of Substrate, the representation itself is less important, because the amount of bytes of data that we're talking about when we're talking about instructions is going to be several orders of magnitude or more or less than something like data. And so having different representations in memory versus on the wire, not a big deal here. But you want something that is independent of a particular language. So I can move from different contexts that are written in different kinds of languages and still work with this representation. On top of that, we also wanted to have a very clear definition of plans, and have plans that are basically self-contained, have clear intention, and really allow for dumb consumers. One of the challenges with working with SQL is that you need a fairly large amount of information to try to figure out what's going on. There's complexities in terms of, like, for example, like figuring out what ambiguous references are referring to, and being able to have metadata associated with all sorts of different possible contexts. There's figuring out whether or not you're going to be doing something like an implicit cast based on which function you're binding to. And so you can actually find a substantial amount of complexity in turning a SQL query into something that is more canonical. And so rather than focus at that sort of abstract level of SQL, we said, you know what, we want something that's much more canonical by definition, so that a consumer of these plans can be relatively unsophisticated. Basically just say, okay, here's exactly what I need to do now, I'm going to go do it. So in order to build this, we came up with a structured hierarchy of primitives, which I'll go through in a second. And we also said, okay, well, for each of these kinds of primitives, there's going to be this common primitives that everybody uses, but there may be examples that are unique to particular situations. And so we not only want to have common primitives, but we want to have what we call extensibility with discipline. And I'll get into that in a little bit. So let's talk first about the primitives in Substrate. So in Substrate, there are really kinds of four main things. There are data types, there are expressions, there are relations, and there are functions, okay? Now, these can decompose quite a bit. So when you talk about data types, Substrate includes a bunch of the standard data types that everybody knows about, right? You've got different sized integers and floating points. You've got various string types, fixed width and variable width. You have complex types like arrays and structs, and maps. So you've got a number of different data types. You then have expressions. Expressions are different ways to work with scalar values or values. And so you have things like case statements and this ability to identify a particular field that you're going to select from, the ability to express literal values. And then you have relations. And so relations are common set operations like a join or an aggregation or a projection or a filter or a scan or / read or write. So we have those kinds of concepts, and then we have functions, and there are several different kinds of functions. There are scalar functions, there are aggregate functions, there are window functions, there are table functions, which are all pretty common concepts that people know. You take these different primitives, you put them in a plan, and then you serialize that plan. The plan itself is serialized in both. We have a binary representation, and we target having a text representation of the plan. The binary representation is built on top of protobuf because that's a pretty standard thing that has tooling available in most languages. The text one we want to build, but we haven't yet gotten started on. So that's the main set of primitives that you're working with. And then as I said, one of the goals with Substrate is that you want to also have extensibility with discipline. And what we mean by this is that we don't want to just have black boxes, because that makes it very hard. As an interoperability format that's going to work between different systems that may not initially know about each other upon implementation, we need to have ways to allow extensibility to occur, but allow systems to better collaborate around that extensibility. So the way that we decided this is kind of a couple different layers. The first one is that, as I mentioned in the previous slide, a bunch of the common things that you know about, like 32-bit integers or an aggregate operation, are defined in the actual project, because we think that most projects will work with these things. And so the goal being this is that many common patterns can be done from scratch with just the things that are inside the project. Okay. On top of that, for each of the different kinds of primitives, we define how you can add extensibility. And we don't have a rule that all extensibility has to be defined directly inside the Substrate project. So when we say discipline around extensibility, one of the key things that we're very focused on is the separation between optimization and semantic differences. So there are often cases when you're working with a query plan where you want to communicate additional information to, say, an engine. You want to say, hey, I think that this is probably going to be approximately 10,000 records, or I think this is going to be highly selective, or I think that this is probably going to use a large amount of memory. Those kinds of things can be very helpful for engines to be able to better configure how they're going to work. But if you were to take that same plan and hand it to a different engine, as long as the engine accurately returns the right data, the particular dynamics around how it did that, how much memory it used, maybe if it spilled the disk or not, are kind of in the noise in terms of like the impact, the result, right? They may impact resource consumption or performance or something like that, but they don't impact result. And so we consider those things optimizations, right? Things that a consumer can ignore and still be okay if they don't understand how to deal with that extensibility. And then there are semantic differences. Let's say we defined a new kind of operator, which is a three-way join. And the three-way join operator has 3 different set inputs, and then it does some kind of specialized pattern around that join. If I am consuming a plan and I don't understand what a three-way join is, I can't consume that plan because I can't correctly return that data. There's no knowledge around what that extra operator means so that I can figure out how to return that data. And so really saying like, hey, let's make sure that we have a very clear definition of the separation of these things. And then the second thing is that when systems are communicating, when a producer is communicating to a consumer, you also want to have a clear way for them to sync the definitions around their extensions. What is it that I'm referring to when I say X? And when I say X, we now know that both of us agree what X means, right? And so the way that we've done this is that we've done it a little bit differently for different kinds of things because they have different needs. So in the context of data types, we actually support 2 different kinds of concepts. The first is what we call physical variations of existing types. So for example, in many systems, you might have both row-wise and columnar-wise representation of the same data type. We consider those to be different variations of that data type. And we define ways with variation to define whether or not those things are compatible, transformable, and whether they can use the same functions or not, if they have disjunct sets of functions that they can work with. And then we have the ability for you to define extension types. Extension types are defined in YAML, and you can use these extension types to define what the structure of the type is, what the name of the type is, as well as use these things to say, hey, I want to use this in a function or an expression or whatnot. And the way it works is that you can define this YAML, And then when you communicate a plan, you reference the location of this YAML with the URI. So that means that a consumer can either, bring the values that are in that YAML, or they can potentially go out to that URI, download that YAML, and work with it there. We also have functions and different ways to extend functions. And so in Substrate, we actually decided that functions themselves are so common. There's so many different functions that people will have that we choose to define these all via YAML. And so we have a standard referencing scheme to those functions. And so we can say, okay, this is the definition of how a function works. And as part of the definition of functions, we declare what are the argument types that the function will accept, as well as what is the output type derivation rule. So if I take a function and I pass in a particular set of arguments, well, if it's a simple function, let's say like adding two 32-bit integers, well, the output type is probably a 32-bit integer in most systems. But then there are more complex calculations, like when you're adding various precision and scale decimals, how do you actually derive the output types? So functions define how you define output types. And then we decompose functions into two main categories. We have functions which are effectively pre-registered. So this could be a function that we know we've defined in the Substrate specification. It could be a YAML you create and add to the specification for your own purposes. And that's a function that's used by many, many different users. The second kind of function is what we call an embedded function. And this is an example where the plan itself contains the logic for the function. So for example, in data science activities and in data frame APIs, this is a very common pattern where you might say, I want to select some data, and then I want to aggregate it, and then I want to apply some kind of mapping function that I've written the Python code to use. And so I want to submit that as part of my plan. And so what we call that an embedded function, because it actually, the plan carries the instructions for how to do the operation, as opposed to just a pointer to the operation. So most functions are pointers, but sometimes you're going to have embedded functions as well. And so we are in the process of defining that in the specification in addition to pointer functions. We also have relations. Now, relations are a little bit more complex in the way you have to extend them because they have arbitrary complexity to the structure of the fields that you're going to have. And so we have a bunch of relations, as I mentioned, in the project already, but then you can define new relations with serialization extensions. For example, in the protobuf, you define those using a combination of any and your own protobuf objects. And again, just like with functions, we are expecting to have both user-defined relations as well as embedded patterns. So for example, I want to express some kind of set operation against my data, but I want to do that with user code as part of my plan. And so again, we're trying to define the embedded pattern around this so that things are not just for SQL queries, but all sorts of patterns that we see in other data computation contexts outside of traditional SQL. So let's talk a little bit about project governance. So the governance of the project is very much a consensus-driven project. Our goal is all collaboration, decision-making is done in the public. We're very much focused on making sure we have a diverse collection of organizations that are involved in the project. And we also want to make sure that it's very clear that the project is Apache licensed today, and it will always be Apache licensed. We're not going to change our spots one day like some of the more commercial-oriented projects like Redis or Confluent have done. So as I said, it's Apache 2.0 license. It's a GitHub project. And we have active contributions from several different companies. We are thinking about whether we should move to a foundation like Linux Foundation or Apache Foundation, but we're really kind of waiting to see as our contributors form whether or not we will do this or not. So in terms of the different parts to Substrate, we have our core components, which include the specification and format. We have the language-specific helper libraries, which are not required, but can help you work with the objects depending on which language you're working in. We also have a plan validator project, which you can take a plan, hand it to the validator, and the validator will identify any problems with the plan when that plan doesn't match the specification. We have integration tests, so you can actually test out whether or not different tools are working, different implementations of Substrate are working together. And we're actually in the process of adding a network protocol. So this will be built on top of, this is being built on top of the Aeroflight SQL protocol. And then we have a bunch of integrations. So as I said before, when we started the project a year ago, we had all these different theoretical integrations. Well, the good news is that we've actually made a huge amount of progress on a bunch of these. And most of this project actually happens in various different other projects, not in the Substrate repo itself. And so I've actually identified separate different places where we're actually making great progress with links there. So I'll share the slides after the talk, of course, but really a lot of progress in a lot of different places in terms of being able to use Substrate in the ways that we hope to be able to use it. And so I'll just leave it with the last thing, which is that we really love you to join the community. Start using Substrate, take a look at the different integrations and examples. There's a lot out there already. Join the community, start a discussion on GitHub. We have a Slack. We also have a Google Groups, which is not linked here, but it's linked on the website. So we'd really love to have you join the community and try it out yourselves. Thank you.